wrap up with chapter 1 tonight. I know we had a bit of a weird disconnection. I think I closed the class by accident last time, and then I struggled to get back in. But in any case, I think we can go on. I think last we started looking at resonance, and we pretty much looked at how resonance occurs, and that it's essentially the exchange of energy between the capacitor and inductor in the circuit. And yeah, so we could actually go and calculate the resonant frequency for, let's get my pen, so we can actually go and calculate the frequency of resonance, of resonant frequency, using this formula. So you guys should be familiar with this formula by now. It's a formula that you guys should have, well, depending on what level you started, you should have seen this formula from anywhere from N3 up to well, now. And then we also looked at the natural oscillation or natural frequency of oscillation for an RLC circuit. So you guys will notice if, so this formula is very related, or these two formulas are related to one another, but the natural frequency of oscillation will always be less than the resonant frequency. All right, so we're using this formula now, or using the natural frequency of oscillation. There's quite a few things that we can go and do. Right, so one of the things that we can do with this formula is determine whether a system would be critically damped. So basically this red curve that we have here is a critically damped system. And let me maybe just highlight the things for us here. So critically damped. Now, if you take a look at a critically damped system, this would occur if we take a look at our natural frequency formula there. This would occur when these two terms are equal to one another. So in other words, you have a 0 under the square root there. All right, okay, and then we also have overdamped systems. Now, overdamped systems, that's going to be the blue curve here on the graph. So yeah, so okay, actually we're still talking about critically damped systems. So critically damped systems, again, the energy stored is dissipated through your resistor before the current can reverse. So there's no reversal of current, but the circuit is also essentially on the verge of becoming oscillatory, right? So you at the border, or basically at the boundary of having an oscillatory response versus a non-oscillatory response. Then you have an overdamped system. Now, overdamped systems typically, just from the natural frequency formula, that is if this, what I would like to call the resistive component, if that is bigger than your reactive component, then your system is going to be overdamped. And yeah, so that means that your circuit response is slow and sluggish. That's due to the high resistance. So the bigger the resistance, the slower the discharge from your capacitor and inductor is going to be. Right. So it also, a big resistor also eats up quite a bit of energy as well. So if we take a look at the curve, or at the graphs here as well, so you guys will see all these graphs are plotted time versus amplitude. Now this is, yeah, so in this case we're looking at the capacitor voltage, but yeah, you can actually look at, yeah, this is if we take the output across the capacitor. Now if you, yeah, so this is essentially, we basically have a step change. So let me maybe just explain this. So basically I have a step change from 10 volts down to 0 volts. Right, and this is basically the response of your circuit, what we're measuring here. Now, this response can be the other way around as well. You can have a step change from, let's say, 0 to 5 volts, but then the oscillation and settling point will then be around 5 volts. Just to explain that real quick. All right, and then we also have the an underdamped system. So underdamped systems, yeah, so for underdamped systems, the resistive component of your formula is smaller than your reactive component. Typically, an underdamped circuit or underdamped system will have a very quick response, and yeah, and you will have a little bit of oscillation occurring as well. And yeah, so also what, yeah, so because the resistance component is quite low, means the resistance is going to be low as well, so they're resulting in the oscillations. So you're going to have a period of energy exchange between the capacitor and the inductor. Now, I also just want to make mention here, it's not necessarily that you guys need to know this, but just keep in mind that this kind of behavior is not just applicable to circuits, but it's applicable to mechanical systems, chemical systems. So anything that will have a change, um, yeah, essentially that's actually pretty much everything in the world. If there's a change in input, the system is going to respond to it in a certain way, right? So depending on what variables and what components there are, the system is going to respond accordingly to a change in input. Now, with that said, I just want to maybe help you guys picture this a little bit better. Just maybe take a look at a few examples, or rather, I'm going to ask you guys for a few examples. So thinking of a critically damped system. So what you guys would know with a critically damped system, so if we just quickly take a look here again, is that a critically damped system of the three here is actually quite a fast system. It's definitely faster than a overdamped system. So especially if we take a look at, let's say, how quickly it reaches it, what is it, the 63.2% value or time constant value that we usually look at, which is around about there. So that is, yeah, so that actually reaches it quite quickly, actually much quicker than what an overdamped system would. So there's a good balance between time of response and, how can I say, um, uh, smoothness of response. Yes. So can anyone name me an example of a critically damped system? And I'll give you guys a tip. There's actually a machine that you guys pretty much use every day. For those of you that have driving licenses, that has all three of these systems in them. Now, so let's think car. What in a car can be considered a critically damped system? So something that needs to have a quick response to a change in input, but not so quick to cause oscillation. Okay, so your car's basically your car, the engine as a whole, right? So that the fuel consumption, you stepping on the accelerometer, that all consists of one system. So when you step on the accelerometer, your car speed doesn't jump to 100 kilometers per hour and there you go. It takes a long time to get there. Now that is an example of an overdamped system, right? So you step on the you step on the accelerator up to a certain point, but it takes the car a significant amount of time to get to the speed to which you have stepped the accelerometer in. Now, what would be a critically damped system then in that case? It's essentially the opposite of acceleration. When you just step on the brakes. So when you step on the brakes, your car needs to be, yeah, so you guys will notice then, as soon as you step on the brake pedal, there's a reaction from the car. But again, the brakes are such that you don't come to a stop. You don't drive slower, faster, slower, faster. You drive slower gradually, and in a very short span of time. In an underdamped system, there's actually quite a few in a car. So you think, might even help you guys, actually quite a lot of your safety features in the car are actually underdamped systems. Because it's usually with applications where you don't really worry about oscillation, you just worry about speed of response. Things like, believe it or not, seat belts, airbags. So if you look at an airbag, for instance, in slow motion, when it deploys, there's a little bit of vibration or a little bit of oscillation going on there. You have, where else do you have it? I want to say you have it with, what is it? ABS braking, but ABS braking is more actually a modified, I want to say a modified critically damped system. But yeah, but essentially, yeah, so that's just to try and have you guys picture what these, what overdamped, critically damped, and underdamped means. All right, so let's just quickly take a look here. Yeah, okay, so one of the things that we can take a look, or that we can see here as well, especially with an underdamped system, you guys will, I hope you guys will notice that the peaks of the oscillations will decrease at an exponential rate. Right, so even if you're going to, let's say, for instance, you run this through a rectifier, for instance, so if you make that wave positive wave, you guys will see that it will, these waveforms will decrease at an exponential, so sort of form an exponential curve with the peaks. Anyways, right, so each successive peak is going to decrease then exponentially, and yeah, so as time goes by, as you guys can see, the peaks of our underdamped system here will grow smaller and smaller, and yeah, so the rate of oscillation decay, so how quickly the oscillation dies away, is determined by what we call our damping factor. So it's usually indicated by a little squiggle that you guys can see there, and then we also have what we call the decrement, or basically the ratio by which each successive peak decreases. So basically, if I now go and I mark this peak here as peak A, that as peak B, that as peak C, and that as D, then the ratio of A to B is going to be the same as ratio C to D. Right, so if you take the absolute value of that peak. Right. So peak A here is almost minus 5 volts. Peak B is probably around 2 volts. Just eyeball it a little bit there. So that's 5 divided by 2. Then C looks like it's like 1 volt, and D might be, yeah, might be even less than 0.5. But yeah, any case, so the ratios will be more or less, yeah, so they will be the same. So ratio of A to B will be the same as C to D. And then if you had more oscillations, then each pair of peaks, the ratio of each pair will then equate to one another. And I also want you guys to take note here is that the period of these peaks, or periods of the period of the oscillations, do not change. So there you have one period, there's the second period. So as you guys can see, it's the same. So the frequency doesn't change. Right, so we can also write this constant here of the ratio between peak, or ratio of successive peaks. We can also write as exponent, or e to the power of minus pi times r over omega L. Now omega in this case, that would be 2 pi times the frequency of oscillation. So that's going to simplify the formula a little bit here to e minus r over 2L. F. Yeah, almost forgot about the frequency there. Right, so that then gives you the logarithmic decrement. Right, so the logarithmic decrement, that is equal to R over 2LF, or pi times R over omega L. Right, so where omega L is 2 pi times the frequency. Right, so that's your logarithmic decrement. And yeah, so essentially, or rather in theory, these oscillations continue into infinity. They never really die out, as well, theoretically. But in practice, we need to, at some point, determine whether or not the response is good enough for us to use in a practical sense. Now, typically, also depends on what industry you work in as well. But I believe for this, for the syllabus that we're working with, we're going to use what is it? Yeah, so we're going to use 1% of the initial peak value as our guideline here. So if, let's say, for instance, peak, yeah, so there should be a peak E here. So if, let's say, peak D is 1% of this value, or actually rather 1% of the value here, then we can actually, after peak D, we can consider the response to be in steady state. And then we can actually essentially ignore peak E and any other subsequent oscillations from there on. So yeah, so this is just to make it a bit more practical when you apply these systems in the field. So yeah, so if peak E was 1% of the peak value, then obviously that will then be considered as our 1% of our initial peak value. And yeah, so in order to determine the number of oscillations that it will take to reach that value, that is then just going to be 1 plus ln of 100 divided by the logarithmic decrement. Now you can take this even further. I don't think in the slides I'm taking this further, but now that you know the oscillation, so usually by this point you also know what the natural frequency is. So if you know the natural frequency, so let me maybe write these things down for us. So you knew the natural frequency, now you know the number of oscillations. You can now actually go and calculate the time that it will take for you to reach steady state. Right, so you know the number of oscillations to 1% of the initial peak value and the frequency. Actually, I need to say Fn here. So yeah, again, you can go and calculate the time that it will take for this whole response to get to steady state. So essentially what you still have to calculate before you get your total time is you just need the time of one oscillation multiplied by the number of oscillations. And that time of one oscillation you can actually get from your natural frequency. So with that said, I think we can take a look at an example. I'm just going to quickly go to the whiteboard and we can quickly take a look at this. Right, so there is our problem. Right, so we're told we have a capacitor with a value of 20 microfarad that's fully charged and is then connected in parallel with an inductor with a value of 40 millihenry. So this is essentially changing circuit parameters that we have here. So the first thing that we need to go and calculate is the highest value of resistance that will allow oscillations to occur. So we basically need to get a resistor size where the circuit is just not critically damped, like barely not critically damped. So it's just slightly underdamped. Okay, so need to go and do is we can actually use our natural frequency formula. That's actually one of the formulas that we will have to use here. 1 over LC minus R squared over previous 4L squared, if I remember correctly. All right. Okay, so for the system to be critically damped, R squared over 4L squared needs to be equal to 1 over LC. Right, so we want to calculate that resistance value. So this is, yeah, so basically we're actually working with 25.1 here. So we manipulate this formula a little bit. R squared is then equal to 4L squared over LC. So we can get rid of one of the L's there up top. And then if we take then the square root on both sides, end up with 4L over C under the square root. That's saying 4 times, okay, so 4 millihenry or 40 millihenries, that's 40 times 10 to the minus 3. And we have a 20 microfarad capacitor, which is then 20 times 10 to the minus 6. All right, so there's an example in the a worked out example in the textbook. I would urge you guys to just go through that. All right, so let's just see what we get here. So yeah, so we're going to get a resistance here of 89.443 ohms. Right, so this is the resistance for a critically damped system. Now, if we read our question, we want the highest value of resistance that will allow oscillations to occur. Now, this means that we just want a slightly underdamped system. Now, the methodology in the textbook is basically that we round this number down, where you get rid of the decimals. So your final answer would then be 89 ohms. Right. Then 25.2, they want us to go and calculate the logarithmic decrement. The logarithmic decrement, that is then going to be pi times r over omega L. Right, so we are running into a small problem here because omega is equals to 2 pi f, and we are going to end up with using the frequency here. So we need to go and calculate what our natural frequency is going to be. Right, so let's start off with that. So natural frequency. So we have enough information to do that now. That's going to be 1 over 2 pi, 1 over LC minus r squared over 4L squared. Substitute our values. That's then going to be 40 times 10 to the minus 3, divided by 20 times 10 to the minus 6. So that's going to be a massive value. Minus, so now you use this value here, 9 squared over 4 times 20 times 10 to the minus 6. No, sorry, that's not 4, it's 40 times 10 to the minus 3. There we go. Right, so if we substituted everything there, we can then go and calculate what our frequency is going to be. Yeah, so you guys can double check me on this. What I'm getting here is 683 hertz. Right, so we can now go and calculate our logarithmic decrement. We now have enough information for that. Right, so calculating the logarithmic decrement, that's then going to be, okay, so I'm going to immediately just substitute everything in here. So that's pi r over 2 pi f times L. That's then going to be r over 2fl. That's going to be, yeah, so you use this value the whole time now. 89 over 2 times 17.683 hertz times 40 times 10 to the minus 3. And that's going to give us a logarithmic decrement here of 62.914. Right, so this thing doesn't have a unit, because remember the logarithmic decrement is essentially just your ratio of peaks. So it's not, no, so we don't really, so there's no unit here. All right, so the next thing that we need to go and calculate is the time that it will take for our oscillations to reduce to 1% of the initial peak value. So we can go and calculate that as well. Right, so in this case, we need to know what our number of oscillations is first. The number of oscillations, that's going to be 1 plus ln of 100 over your logarithmic decrement. So ln, yeah, so ln of 100, oh goodness, over the logarithmic decrement that we just calculated as 62.914. That's going to give us, so you can actually have fractional oscillations as well, that's fine. And this is going to give us 1.073 oscillations. All right, so another thing that we now need is we need to know what the period of one oscillation is. Let's see, let's pick a different color, try and pick a different color here. So the period of one oscillation, that's just going to be 1 over 17.683. And that's going to be 56.551 milliseconds. Right, so now we can actually now go and calculate the total time that it will take for our oscillations to get to that 1% value of ours. Right, so that's then going to be the total time taken. That's then going to be En multiplied by N. That's 56.551 times 1.073. And that's going to give you a total time here of 60.679 milliseconds. All right, so there's the problem solved. All right, any questions?